and move your laptop. Oh. All right. Now we have to do this swappy business. And I'm a bit echoey, aren't I? Can you? And with a bit of luck. No, yes. Almost. So now I have to do a, I think if I do duplicate, that sometimes works. Is that good? Oh, that's not good. Now you're just getting this kind of game. All right, let's try again. This, as ever, this worked perfectly well before the screens went down. Okay, good. All right, are we good to go? Can you hear? Is it too loud or no, it's okay. It's okay, thumbs up. Excellent. All right, start the stopwatch. We have 50 minutes to learn about linear types. So I don't know about you, I find linear types extremely confusing. They're sort of attractive, alluring, something like an Escher diagram. You look at them and you think that's extremely cool, and then you find you've sort of arrived back where you first began. So look at this. So if you search for linear types in Google Scholar, you get 750 results, and with Phil prominently at the top for some reason. If you search for linear logic, you get 3,700 results. So this is an area dense with related work. And that's because it kind of looks cool and interesting. And so with them, despite all this stuff, there hasn't been much delivery in the programming language world, with the notable exception of Rust, which is about which the keynote at Curry On last year was exactly about Rust. And I have Rust envy, of course, because Rust has successfully delivered something that looks like linear types into a practically useful programming language. It is an amazing achievement. What makes it even more amazing to me is the guys who built it did so without first doing an Andreas Rosberg kind of formalization underneath. They just built it. And I thought, when somebody does the formalization, it'll be full of holes. But Derek Dreyer has done the formalization. It's not full of holes. They're just an amazing achievement. Anyway, so thumbs up to Rust. Let's see. There's lots of confusion, too, about what a linear type might be. It's sort of alluring, but people mean many. It doesn't mean one thing. Right? So one, you might say, if this is a linear function from file to IO unit, that might mean that that function must be given the only pointer to that file. Another thing it might mean is that the function guarantees to consume its argument exactly once. And another thing it could mean is this function must be called and will be called exactly once. So there's a lot, when people say I have a linear type, it's not, you have to poke quite carefully to find out exactly what they mean. And then when you ask them exactly what they mean, they tell you something like this. They produce upside down ampersands and exclamation marks and strange new type constructors with circles around them, and that makes my head spin. And it also comes generally with some questions about how can you mix linear and nonlinear code. So the goal of this talk then is to say, how could we add linear types to a language like Haskell, a higher order polymorphically typed language like Haskell, without messing it up, right? And indeed, why would we want to do that? And the whole of this development was driven, the reason that I found this, really wanted to work with these Tweed guys, it was driven by them, not by me. And they were saying, we've got practical applications in which we need linear types in some flavor, and we think we found a way to do it. And I was saying, okay, so that sounds motivating, right? But I will say that this paper, this talk in this paper really only describes one point in the design space. I have not achieved that Olympian view that I understand how all sort of linear type systems fit together. Phil is in that Olympian position. I'm not yet there. So I'm just going to describe one point. I don't even want to say it's the best point, but I will say that it is the only point that I have found in the design space which I feel is retrofittable into a language like Haskell that I've come to understand. So I'm just going to share that journey with you in the hope that you do too as well. So I think it is sort of a language experiment, if you like. Okay? So just to position this, not the silver bullet, just one way that it could maybe all work together. So I'm going to show you quite a lot of code. I really want you to understand it. Please ask clarifying questions as we go along. I hope there'll be time for questions at the end. We're only 2.5 minutes in. So what is this type going to mean in linear Haskell? It's going to mean something like this function consumes its argument exactly once. That's what this little lollipop symbol is going to mean, right? Now, even that's a bit vague. Look at these functions, lambda x, lambda y, x plus y. Does that consume x exactly once? Does it consume y exactly once? So does it, this would be it consumes x once and y once. It consumes x many times and y once. Well, like if you had a partial application and you called that partial application a bit many times. So you might worry about things like this. Or in this function, lambda x, x comma true, does that consume x exactly once? What does this consume once thing mean exactly? So we have to answer these questions a bit more precisely. So this slide is very early in the talk. This is the slide that I would like you to remember because you will need it again and again in understanding everything else that I show you. In this understanding of linear types, if f has type A to B, it means that if the result of the function is consumed once, then, and only then, we're going to promise that the argument is consumed once. I'll say that once again. If the result of the function is consumed once, then we will promise that the argument is consumed once. And then we have to say, what does it mean more precisely? This is still not fully precise. We're a bit more in the paper. What does consume once mean? And that's going to be type directed. So at base types, it just means like int. It just means we're going to evaluate it. For a function type, this is interesting, right? So for a function type, to evaluate a function value once means to apply the function once and consume the result once. So that tells you for this lambda x, lambda y, think of the partial application, so it consumes x and its result is a function, right? If you consume that function once, it means to call it once and consume the argument once. So really, this lambda does have type int, lollipop, int, okay? So it's very, very important that this is, the guarantees only apply if you say, if the result is consumed up, then. And at higher order, this is what it means. Okay, with me so far? This is if you get lost here, you will be deeply stuck. For pairs, then to consume once means to pattern match the pair and consume both the first and the second exactly once. Okay? That's it. So just remember that for everything else that follows. Yeah?
How's the implication arrow in the function going? So if the result is consumed once...
Yeah, it's right. It says at the top. If the result is consumed once, then the argument is consumed once. That's it. Okay, yeah?
So essentially the function f, like if it uses the variable a in an if statement, it won't have another if statement below.
Well, I don't know what it means. So this is a functional language, right? So there isn't really a below in the same sense. But there was a question about ifs. But if it uses its argument in one branch, it must use it in the other branch, if you like, to consume once, right? That means in every execution path. Okay, so let's see. So first thing to note, this does mean it's a property of the function, right? So like a type system, types usually tell you a property of the function. This tells you a property of the function. It is not a requirement that the caller must pass a unique pointer, nor is it a requirement that the function itself must be called once, okay? So fix on this one, not these two. Okay, so let's talk about data structures, because it's super important if we're going to retrofit this into Haskell that has to work well with data structures. So here's a function that takes an int and returns a maybe int. So maybe, here's the data type maybe. It's got two constructors, just and nothing. So if you think of if the function just all by itself as a function, is it linear? Does it have type A lollipop maybe A, or does it have type A arrow maybe A? Well, the data constructor itself doesn't use the value many times. So we're going to interpret an ordinary old Haskell 98 data type as being a linear arrow. Okay. So just passing it to just, that means consuming it once. But of course, to say that this function is linear, like the whole function, that says if the result, this maybe value, if that is consumed once, then it will consume x once. Because if the result of the maybe is consumed once, then the argument will be consumed once. If the result of the plus is consumed, do you see what I mean? Okay, it's all predicated on if the result, then the argument. So, yeah, Phil.
Does this mean I have to go and rewrite all my data types?
No, it does not mean you have to rewrite all your data types, because if you, let's see, if you write them in ordinary old Haskell 98, this is what you mean, right? If you write them in GHC today and don't put some linear types language extension, this is what you mean. And if you do put the linear types language extension, then you have to write them like this. But we're going to see that it's very helpful to have data types that have ordinary arrows in here. So I'll show you that in a sec. Okay? Yes. So, but just notice that this doesn't force some limitation on how you can use just, right? We can use ordinary old pairs which have a linear type, and then this function which takes x and y and swaps them, that has a linear type. If its argument to consume, if the result is consumed once, then the argument is consumed once. But this function g, which, let's see, throws away y, that's not linear. Okay? Yeah, sorry, I didn't write all my slides to be high enough, did I? Feel free to stand up, or there's plenty of space over here. Okay, so I'm going to give you two classes of applications that this kind of thing is good for. Number one is safe mutable arrays. Now, here's the way inside GHC we build arrays. So arrays are, immutable in Haskell, but some way you have to build them. So how are you going to make these arrays in the first place? One way to say that's hidden inside the compiler, which it is, but it's really just the library. And here's how the library is implemented. So there's a function that builds an array, takes the size of the array and a set of index value pairs, and initializes the array with all those index value pairs. Okay, so how does it work? Well, we're going to do in a monad, right, this states monad, I'm going to allocate a new mutable array, call it FMA. Oh, I should have, that should be MA. That's simply a mistake, because I'm then going to, for every element in the pairs, I'm going to write the index value pair into that mutable array. And then finally, what am I going to do? I want an array, and I've got a mutable array. It's a different type, right? This new M array, he returns a mutable array, which I'm abbreviating M array in this thing. But I need an array. What can I do? Oh, I need to freeze it somehow. So to take an M array and gives me back an array. But now what if I froze it to get an array and then used the mutable array again? That would be bad. So maybe I better take a copy. But that would be inefficient. So hence unsafe freeze, right, that says, I'm just going to turn it into an array and you better not mutate it afterwards, right? And that's what happens inside the library. So this is not very cool. Okay? So what can we do that's better? So here's an interface you can write in linear Haskell. So I'm going to spend the next few slides simply explaining this one line of code here. But let me give it to you in outline. So I'm going to call new M array on size. That's going to give me an M array, right, which I'm going to pass to this function. Right? So this MA is going to be that mutable array. And then I'm going to, over that mutable array, I'm going to fold some writing stuff that's going to successively update it. And then finally, I'm going to freeze the result. So in outline, I hope that's clear enough. I'm giving you the types of all the functions here, but I'm not expecting you to read those types yet because I'm going to go through that one slide at a time. But I just want to get the big picture up here. That's what we're doing. So we're implementing the very same array here, but without the unsafe bit. That's our goal, right, is to be able to write code that was previously unsafe. We're trying to shrink the trusted code base. Okay, so let's start with write. So what does the function write do? Here's its signature. I gave it here, but this is just copied here. It takes an M array and an int a pair, and that's just an ordinary pair. So its arrow, right, it doesn't need to be linear. The list of index value pairs doesn't need to be linear. But write guarantees to consume the mutable array that it's passed, and it returns a new mutable array, that is with the mutation performed. Okay? So what that means is that every write returns a new array, and because it's consumed, if I was to attempt to write something that I might schematically write like this, write into an mutable array and then write into the same one, that would be rejected because I've used this thing twice, but each of these guarantees to consume it once, and as we'll see, this overall function, as we'll see, guarantees to, it takes a mutable array that it must consume exactly once, so I'd end up consuming it more than once. We haven't seen that part yet. Okay, so what that does mean is that you can't write code that says write. You have to sort of do this threading business. Each write returns a new array, that it goes to the next write, returns a new array, that returns to the next write. So you sort of threaded the data value through, okay? And that's a bit inconvenient in programming, but it's just the price you pay, and pretty much every linear system requires a price of that kind. And as we shall see, it actually is quite useful sometimes. Okay, but anyway, it's just the price you pay. I'm sorry. We're not going to get everything. So far, so good? Oh, yeah. So we can do rusty things. I'm going to come back to Rust. Right, so I'm just going to tell you about this point in the design space. Okay, so what does new M array do? Well, it takes an int in this continuation thing, this function, right? So new M array makes a new mutable array and gives it to this function, which guarantees to consume it exactly once. I'm going to tell you what this unrestricted bit is at the end. But But you'll notice that I couldn't make new array sort of return, what type would I give new array if I'd have no way to say this mutable array is a very vulnerable thing, right? I can't duplicate this guy. The only way I can say this new array is making something that must not be duplicated is to use this kind of continuation passing style. So that's another price we're going to pay. As soon as you're building something that you really want to guarantee that it will never be shared, you must use this kind of CPS. And it's a consequence of this particular way of setting things up. Okay? So now I hope you can see that because I set things up like this, then this write is doing the consumption, and so I can't feed it to something else. Okay? All right. So yes, that's right. So I'm just wanting to point out here that I don't have to return some special kind of array. This is just an ordinary mutable array, right? But the magic that means that it's not shared is the fact that it's in the context of this continuation that requires this guy to be consumed exactly once. Okay. So what about read? What are we going to do for read? Well, read had better take an M array, and just like write, it had better consume it and return a new one, and of course the value that it's read. But now we have a bit of a problem, right? Because we're going to want to consume this guy exactly once, but the thing we read, we don't want to consume that exactly once. Right? Because they've got this mutable array, which is this vulnerable thing that I mustn't share, but the things it contains might be just integers or trees or something that's perfectly shareable, right? So the status of this component of the result is somehow different than the status of this component. So what am I going to do? So I'm going to declare a new data type, unrestricted. So this is getting back to Phil's point. And this data type, unrestricted, is just a regular data type, and here is its definition, and it unusually has a non-linear arrow in it. So now read is going to return one of these unrestricted things. And what that's going to mean is when I call read, well, I'm going to have to pattern match on the result. First, if it returns a pair, I get a new mutable array and an unrestricted value here. And then I feed MA1 into the second read. I get an unrestricted value V2. Okay? I think you can see that the types match up. But what is this unrestricted guy, and how is it helping us? It is, by the way, essentially just bang in linear logic. I mean, it's not a new language construct in this presentation of linear logic. It's just a data type with a nonlinear arrow in its type. So I have to explain how does pattern matching get changed by what's the significance of having a nonlinear arrow here? So then the way its significance is this. When I said what exactly does it mean to consume a value once, I said for pairs it means evaluate the pair, pattern match on it, and consume both the arguments once. So I'm going to modify that slightly to say evaluate the algebraic, the data constructor, pattern match on it, and consume each linear component once. That's very clever. When Arno first showed me that, I thought, that's brilliant, right? So, because for pairs, remember, it had a linear type, so I was obliged to combine them. But for unrestricted, I have no obligation to consume the component of the unrestricted thing. I consume it 0 times, many times, as many times as I please. So it's a way of sort of switching off the linearity for that component. Okay? So here, this claim, right, so here am I using x twice. So this is a linear pair. So to consume, let's see, how can I say this? If I consume the result of this function once, am I consuming y at all? Well, I'm not consuming y at all, but I'm obliged to consume the argument once if I consume the result once, and I'm not consuming the argument once, so it's not linear because pairs have a linear type. But if I do something very similar here, actually, I should have really said just 3 here, shouldn't I? That would have been better. But maybe I'm consuming x more than once here as well. It's the same thing, right? So here I don't, there's no restrictions on what happens to x. That's why it's called unrestricted. Okay? So this is the thing to remember, that the obligation is, if you evaluate the result of the call once, then the argument is consumed once, and the argument is consumed once. This is the rule for algebraic data types. which just gets switched off for any data types that are defined with a nonlinear arrow. That's kind of nice because it's a way of saying all the existing stuff will work quite well, but you get this extra bit of control that, as we'll see, is extremely useful. Okay? Right. What have we got to? Good. So now you might wonder, let's talk about that. There was another use of unrestricted, not just in the type of read, but you remember new array also contained this unrestricted. Why was that? Why did I need an unrestricted there? Well, in other words, could I give it a type like this? Well, the thing is, UMArray applied to two things, so S and a continuation, only makes guarantees about this array if K applied to MA is consumed exactly once. K applied to MA is going to be this B thing. So I'd only get the guarantee if I knew how the consumer was going to consume the result of the whole thing, but I don't. So by giving it a type like this, I say, no, I don't really care how this value, which might be an ordinary old vanilla array, is consumed. So this is a way of having the right type to new M array that doesn't require you to say anything about the caller of new M array. It's all in here. Okay. All right. So now the last piece of this. So we've talked about new M array. We talked about read and write, and we should talk about fold. So now fold is a little tricky, isn't it? So it's taking this MA, which is this sort of linear value, this mutable array that's very vulnerable, and we're trying to, thread it through all these folds or this sequence of writes. But to do that successfully, we need fold to have this type. Right? It's taking this write guy, and it's going to, or a type similar to the key thing is that he's got to take the first arrow must be linear. Right? Because he's got to consume this MA guy, you've got to consume him linearly. Right? So this guy must be linear. And he can only be linear if the function you're using to compose all the elements together, remember what fold does, it takes all the conses and nils and replaces them with the k's and z's, or if it's a fold L, so it's the other way around. Okay? So the linearity of fold L depends on the linearity of the argument that you pass it. Well, in this case, we're good, because write really is sufficiently linear. But that's a bit scary, because now maybe we need another fold L. That's not very satisfying, is it? And the code for the new fold L would be the same as the code for the old fold L. At which point you all shout, polymorphism! Yes! That's our solution for taking functions that have the same code but different types, right? We just like to give it one type to rule them all. And indeed, that's exactly what we can do. We want, fold L has both of these types. In fact, it has some more types beside. So we'd like it to have a type like this. For all P and Q, a arrow sub P, so what are these arrows sub P and Q? So ordinary arrow is going to be arrow sub omega. Omega means you can use me as many times as you like. Lollipop is going to be short for arrow sub 1, meaning you must use me exactly once. And arrow sub P means I'm really not going to tell you whether I'm omega or 1. I'm universally quantifying over that, right? If you call fold L with a function that has arrow 1, well, then you get an arrow 1 here. If you call fold L with a function that has arrow omega, you'll get an arrow omega here. And I think it won't take you very long to figure out that actually the P and the Q do not need to be the same. I wrote them the same, perhaps sloppily here, but in fact they do not need to be the same. They're quite independent. Yeah?
How do I write subscripts in Haskell?
How do you write? Oh, so there's a concrete syntax thing. I'm going to ignore concrete syntax. But mutter, mutter, Unicode, mutter, mutter. I don't know. But, okay. Are we good? So at this point, I thought, okay, so now something is coming right. When you see that you can use polymorphism, which we already have, we can reuse all of the machinery of polymorphism and most general types and all of that kind of stuff. Now you think we're cooking with gas. Okay? And moreover, note that this list is the ordinary list. This is the very same list that we have in Haskell today with those, with its constructors interpreted as linear things. And it's the very same fold L. We've just re-type checked it and inferred a more general type than we had before because now we've got this linearity polymorphism. Okay? That's the deal. So that now you sort of sense the thing, you're going with the grain when you see things like that happening. So let's just say the same again. So lots of functions then get nicely generalized types. And you could come up with all sorts of UI things. Do you want to show the novice programmer a type like this? Probably not. But that's it. That's now it's the type it morally has. And moreover, Haskell already has grown zillions of kinds of polymorphism. We have type polymorphism. We have kind polymorphism. We even have levity polymorphism. So hey, linearity polymorphism is no big deal, right? So as it were, it's a price already paid. Whenever anybody says something comes for free, what they mean is it's already paid for, right? So this is already paid for. Okay. Yeah.
You had a board on the previous slide that's erased. It's already
That said what?
at the bottom. It's
Oh,
always erased.
yes, like all polymorph, like all type stuff, none of this happens at runtime.
Would it ever be useful to be able to cast away and then dynamically cast?
Would it be useful to do something dynamic? Ask me at the end when we get to questions. That's sort of deeper than clarification of yes. Okay. Otherwise, I'll have a brain aneurysm, and that would not be good. Okay. Good. Phil.
What is levity polymorphism?
I will tell you at the end. Ask me at the end. But it's extremely cool, and you should have it. Second class of applications, I want to show you a completely different style of application for this kind of thing, and that is to do with I/O protocols. So there's a whole class of these things. Essentially, it's resource management. You have a file, you want to ensure that you've opened it, you want to make sure that you do close it, and that you do not use it after you close it. You're doing some kind of manual malloc and free for resources because you've got some 3 gigabyte resource, and you don't want to, you want to be very careful about exactly when you allocate it and deallocate it. You might have some kind of explicit malloc and free, same things as for files. For sockets, you might make sure that you want to open it, then you want to bind it before you read from it, then you want to ensure that you do close it and you don't read it. So there are lots and lots of examples of this kind, right? And there's lots of papers about how to do this kind, how to ensure, give static guarantees for this kind of stuff rather than runtime errors. So here's how you can do this in linear Haskell. So you have we start with a bit of a problem. What does open do? It takes some kind of file string. It's going to return a file handle. But somehow I've got to say, this is a file handle that you can only use once. So I'm going to, for now, just add an extra argument to the I/O monad that says how often you're allowed to use this argument. And I'll explain why that is not a new thing, really, in a second. But just bear with me for now, OK? So you should read this as saying, open produces a string and a file handle that you must only use once, right? It must be used in Linux. Read takes a file handle and consumes it, right? And produces a new file handle that you must only use once. In fact, you must use the whole result exactly once. This component, well, we're going to use that file handle exactly once. And so the bit that you can use many times, you have to wrap an unrestricted around for the same reason as before. Close consumes it and, well, returns nothing interesting. And you can use that as many times as you like. And you can write all the other suitable functions here. And then you can write code like, that does sensible file handling things, and that all type checks. Okay? But I have to tell you, I've just snowed you with magic here. Well, what is this magic stuff? How does that work? Okay? But I want to have sort of an intuition that that's the kind of thing that we could do. But now I have to explain, what is the magic? Well, look, this I/O stuff, what is this I/O stuff? Well, when I write open followed by some print using the file handle, as Phil taught us so many years ago, this is just the use of bind, right? The bind in the I/O monad. So really, after desugaring, we get open the file, and this is an infix bind, and here's a lambda. Oh my goodness, it's a lambda, so it can have a lollipop type. And that was exactly what we needed for this. So that one there means that the bind, the second argument of the bind is going to be a lollipop. If you like, maybe I should have written, we haven't done this sort of concrete synonym, arrow lollipop, meaning this is a linear lambda, because it is a linear lambda, okay? Because of this one. I'll show you a bit more about how that works in a second, but does that, so the big win here is that it's another thing of, it came for free because we've already paid for it. We've been we really do this in Haskell, right? So it's already paid for. We already have converted our I/O performing programs into CPS. And so that means that there's nothing really new here. It's just, after desugaring at least, it's just ordinary linear types, okay? And moreover, if you, each bind, so here is the type of bind, right? And it's, and I'm being polymorphic here again in the thing I'm quantifying over, so that's nice. More linearity polymorphism there. And let's see, each bind independently chooses its own, how to instantiate P. So that means in this program, some of them had linear P's, those were the I/O ones. Some of them had nonlinear P's, the omega ones, and they're all independent. It's not that the whole string has to be linear or the whole string has to be nonlinear. You make an independent choice for each line of your do notation, if you like. Okay? And then you think, well, how are we going to implement this? Well, so I'm now going to show you, this is the way GHC at least implements the I/O monad inside. So what is the implementation of IOPA, this funny type constructor here? IOPA is simply short for a function that, it's short for a function that takes a world to an I/O res. What's an I/O res? It's just a pair of a world and a value. All right? So let's see. What's this world? Well, this is like we think of that as being a state token representing the state of the external world. So every I/O operation takes a state of the world and returns here a new state of the world, and that thing is threaded linearly, which we can express because that's always linear here, right? So the state of the world is threaded by this I/O stuff linearly. But look at this. This is now here. The A part, its linearity is controlled by this linearity variable P, which is a parameter of I/O res and a parameter of this. So now we've got data types and new types that have parameters that are these linearity variables. Right? So it's not, that linearity polymorphism we were discussing is not just for functions which have type, for all P and Q, blah, blah, blah. We actually need them on data types and new types as well, as you can see here. So and again, you feel, oh, now we're going with the grain. The things we have already just are working with us. Okay? And as a side benefit, all of the internal machinery of GHC that takes this, this isn't really what's happening in I/O. This state, we don't really pass some giant data structure representing the state of the known universe. It's really just a little token that's threaded through. But internally in the compiler, we have to promise that we're never going to duplicate that token, and there hasn't been a check for that up to now. But now, this type will mean there is a check that we don't accidentally, in some compiler optimization, duplicate the world, which is known to be difficult. Okay, or destroy the world, which is known to be undesirable. Yes. Okay. All right. That's it. That's the. I want to show you a couple of other examples of how how this I/O protocol stuff might play out. So the first one is to do with session types. So the setting here is you're in some kind of dialogue with a remote server. And you want to send a value of one type to him, and he sends you back something, and you want to send him back something of another type, and there's a sort of protocol that you're following. How can we express the protocol? So one way to do that is, which is different to the way session types do it, is to just follow what the PyCalculus did, which is to pass channels in messages. So here, your request to the server might be a pair of a string saying what you want done, and a channel on which the server can reply. All right? And so this is the channel. This says, I'm a channel, and this says, please send a value of type reply 1. What is reply 1? That's the server replying to you, and the server says, oh, my answer to your first request is, here's an integer, but we're not finished in our conversation. You need to send me something of type request 2. And I'll give you a channel to do that. So every message contains, as it were, the channel to reply on. These are all one-shot channels. So then you reply on this rec2, you send the server a character and a channel to reply on, and then he's going to send you finally a reply, a value of type reply 2 that you are expecting, you the client are expecting. When you get that back, the server just said, the answer is 3, and he doesn't give you a channel. That's the end of our conversation. Okay? So it's another way of expressing something that's very like session types. And it's very easy to write this code. So each time you have to make a new channel, and then you send your request to the server. Then when the server replies, you do a receive on channel 1, which is the thing that you sent here. Oh, that should say rchan1. And you match to get out the number he sent back and the channel that the server wants you to send the next item on. And that's what the next time you got something to send, you send it on this. Okay? But of course, the key thing about this protocol is it's very important that you do actually send something on schan2. Right, if the server says, I'm sending you, the channel to reply on, and you say, no, never mind, I'll just throw it on the floor, right? Then your conversation has not come to a conclusion. Or if you were to send two things, one after the other, that would be bad too. Server's not expecting that. So these channels are sort of used once channels, and you can express that very nicely using linear types. Okay, so it's another way in which linear types can sort of, essentially, they make this kind of way of expressing session types sort of watertight rather than just suggestive. Okay? And here's one other thing that you might want to do with sort of I/O and so on, which is usually called tight state. So this is for sockets. You open a socket and you get back a socket that is not yet bound. So you have to do some kind of bind operation on that always takes an unbound socket and returns what? Well, a bound socket. So sockets have a type index that tells you its state. Right? But because, and then read takes a bound socket and returns a new bound socket, and then finally closes it. Okay? So this type index makes sure that you can't read from a socket that hasn't yet been bound, or that you can't bind a socket twice. And that's nice too. And so this is where I said, do you remember where I said that threading business has some advantages? So here it is. The threading business does have advantages because these, the values that I got back, which I inconveniently had to thread, really have a different type than the ones that they were passed, and that's quite convenient, right? In applications like this, it's much easier to deal with than having some kind of tracking of type state implicitly done in the monad on the side. That's quite technologically complicated, whereas this is extraordinarily simple. Okay, good. So now, what are we going to do about exceptions? I'm anticipating that somebody will ask this, because you should. Right? So exceptions are extremely annoying. Well, what does it mean here? If I say, does this function have a linear type? You would say, well, if I consume the result once, then I consume both arguments once. But if x is 0, then I consume x once, get an exception, so I never actually touched y. Oh dear. So what to do? And here in a code like this, I might open the file and I do something. I'm not even passing the file handle to it. Really, all I'm going to do later is to do read line from the file and then close it. That all looks well behaved. But if this do something thing blows up and throws an exception, well, then I haven't closed the file. That's really embarrassing. It's really annoying, isn't it? So in some shape or form, all linear systems suffer from this problem, have to deal with it somehow. So what's our story? Well, one answer, so a sort of non-answer is, technically, we just say that if we have to look carefully at what we're claiming, right? So we say, if the result is consumed once, then something is true, right? So if the result is consumed once, but that process throws an exception, or diverges, actually, then we say nothing. So that's a bit of a sort of casuistry. I'm just saying, okay, so I didn't give you any guarantees if there was an exception. But you might say, but actually, Simon, I want some guarantees. Well, I would like you to close my files, please. And so what to do? Well, so at this point, I'm a little bit on thin ice because I'm not a Rust expert. So please correct me afterwards. But I believe that, so Rust has to tackle with this same problem. And I chose it because it's the leading protagonist of an actual practical system. But I think it's true to say, correct me if I'm completely wrong here, that there's sort of exceptions in Rust have two flavors. One is a sort of panic exception that says something bad has happened, assert has failed, right? In which case, pretty much kill the thread. They're difficult to catch, or maybe impossible to catch. Is it impossible to catch within a thread? Yeah?
You can catch it technically, but it's stronger than you don't.
You can what?
You can, but it's for FFI purposes only.
Okay, so to a first order, the first approximation you can't. So that means that something bad has gone wrong, and you're basically trying to bail out completely. Or you can return, I think there's a special type called result, or some flavor of this, in which the function does return a value, but the value says whether the function succeeded or whether it was an exceptional value, right? And so, so of course, this part, we can play exactly the same game. And so one way to do it is to express it as a different monad. You might call it resource-safe I/O. And so an exception in this monad is just like panic in Rust, and it sort of bubbles all the way up to the top where we can just close any open file handles because they've accumulated when you opened them in the monad. So we can guarantee that we don't leak. You just don't get these stronger guarantees. So we're sort of stuck with that. And you might say, well, so at this point, I would say to Arno, look, so Arno, if you could do this all in, just by writing a library, why are we bothering with linear Haskell at all? Right? To which response is, well, look, this isn't the only library that does these kind of things. There's a library called Resource T that has something very similar nested structure behavior like this. So one also says this doesn't necessarily give very prompt deallocation. So long as you're not throwing exceptions, and the coding standard is, well, you throw an exception if something bad, something catastrophic has gone wrong. Basically, you're in emergency mode. You want to get out of here and start something else instead, right? So in the normal case, you're not going to be panicking, and so you will get much prompter deallocation. Those closes will happen right away, not in some later catch in the monad. You're guaranteed not to get any use after free errors. That's really valuable. The type state stuff that I was showing you for sessions, that's still jolly useful. And many programs really don't worry. That stuff about mutable arrays, if there is an exception, we're going to bail out and the mutable array will just be garbage collected. That wasn't the big point. The big point of this resource stuff is you really eventually want to catch all the leaks. So I think I think the jury's out on this sort of practical stuff, but I think Rust has demonstrated that you have to have some restrictions, and those restrictions don't destroy the utility of linearity. Okay? So, okay, very good. So there is a paper about this. I'm not going to tell you much about the formalism, just to say that the formalism is actually, once you've internalized the main, remember the main slide 3 that I said, remember this? Once you've internalized that, the typing rules are easy to read. So this is for an explicitly typed calculus. So lambdas are explicitly annotated with a lambda, as are case expressions, and indeed lets. And there's the multiplicities are not just one omega in a variable. It turns out you need addition and multiplication of multiplicities. That's actually not very difficult to do. And then let's see. So the typing rule for lambda is fairly straightforward. What do we say? Well, if a lambda decorated, so this pi tells you whether it's a linear lambda or not. It tells you or it might be a variable. It tells you the multiplicity on this arrow. So it ends up straight there on the arrow. And you put into the environment x with type A, and the multiplicity lands up in the environment too. These multiplicities, this pi does not end up in the type A, it ends up in the type environment, right? Think about it, multiplicity attached to binders, and perhaps subscripted on arrows, but nowhere else in types, okay? Apart from type parameters, I guess. So, and then for application, so now if you've got a function of type A, pi b, what have we got to do? Well, we've got to type check the function and type check the argument, and then all I'm going to do is I'm going to need all the resources that the function needed and all the resources that the argument needed multiplied by pi. And you have to just say what multiplied by pi means. So, but the typing rules are actually remarkable. Even I found I could understand them after Arno had explained this to me. So I just want to tell you a very quick thing about something that happened after we wrote the paper, which is that we realized that after compiling pattern matching, we get lots of code like this with join points. So we do some case analysis. If it's A, we want to do J. If it's B, we want to do J. If it's C, we want to do X plus 2. So J is like the code flow has gone together. Imagine this was a big expression. You don't want to duplicate it. But now, is this linearly typed in X? Oh, dear. It is not, because X is used both in the right-hand side of this let and in one of the branches of the case, and that doesn't look linear at all. So you need to fix up your typing rule, at least for non-recursive lets, to take account of this, and that turns out not to be very hard to do. We're proposing to do that only for the intermediate language and not for the source language. So it's just to say that the experience of implementing this in reality had led to further refinements in the intermediate thing. let's just remark that, too, that a lot of this is not very closely constrained to the 1 and omega that I've told you about, used exactly once and used as many times as you like. Right? It'll work on any, what is this? This is sort of semi-lattice mumble, but it just means that you have addition and multiplication with distributivity laws. You have identities on both addition and multiplication and an ordering with the least upper bound. If you have one of those, you can do it. So a system with 0 or 1, exactly 1, and omega, that's another possible lattice that you could use here. So it's quite, the type system is quite well parameterized over exactly the choice of this, and we're not, at the moment we're just sticking to 1 and omega, but you could go wild. Okay? So now, to finish up, I just want to stand back a bit and say, sort of look back at least my, pygmy eye view of the design space. So here we are. The thing that's worked well is a nice integration with existing stuff, right? Higher order functions, polymorphism, and algebraic data types all have fitted together quite well here. And particularly this business about being able to choose independently for each argument, and indeed perhaps polymorphically, this might have a subscript p, that has turned out to be extremely useful. Okay, the second thing to note is we do not have subtyping. So subtyping plus Haskell's higher kinds plus type inference is extremely problematic. I do not know what to do. So in Haskell's type inference engine, at least, we've remorselessly not allowed any subtyping. But you might worry, what happens if G takes an argument of type int arrow int, but you give it an argument of type int lollipop int? G says I need an argument that is just an ordinary old function, and I give it f, which is a super duper linear function. It makes extra promises. G shouldn't mind that f makes extra promises, should it? Right? No, G should not care that f makes extra promises. F, it could make as many promises as it likes. All G needs is that you give it an int, it gets back an int, right? So what to do? Well, one possibility is to say, look, E to expand f, and now it turns out this is well typed. Another possibility, which is a rather better one, is to say, use polymorphism, don't use subtyping. Wherever you want to use subtyping, naughty, use polymorphism instead. So f probably has this type, right? It actually works for any p. So a lot of functions get turned into linear, and then you really can apply G to f. So it just wasn't obvious to me at first, but it kind of works out quite smoothly. Here's another way of looking at the design space, right? So, and this I'm going to use my last few minutes to describe. There are sort of two somewhat orthogonal axes in which you might understand linear types. One is, have you got linearity on the arrows? That's what we're doing. Or have you got linearity on the kinds? I'll say what that means. And the other thing is, are you using linear types or uniqueness types? So let me say, firstly, about this axis here. I've been describing linearity on the arrows all the time. What does linearity on the kinds mean? It's the first thing you would think of. Right? It says, look, new M array returns a M array. And M arrays are these precious things that might not be duplicated and might not be destroyed. Right? So a property of M array is that it's a sort of careful thing. File handle might live in that world as well. So it's a property of the type that it must be not be duplicated or destroyed. And so whenever you've got something that's a property of the type, you might say, well, we got a kind system to classify types. So maybe we should use the kind system to classify types into the ones that must be used linearly and the ones. So let's say int has type star, that is type, and M array has type star star, that is non-duplicable type. That seems like a plausible story, right? But then, lots of questions have, can we have lists of things? But lists, what's the kind of the list constructor? Does it take stars or star stars? And are you maybe going to be polymorphic over that? And what might that mean? And what about pairs that have a sort of mixed economy here? Then you might ask whether, this type, what is the kind of list of T? So firstly, is this type well formed? And you might also ask, what is the kind of list of T? Is it linear or non-linear? But we've clearly seen that we do need to have linear lists. So the rabbit hole gets quite deep. And here's an example of it getting even deeper here. Consider this. Supposing f has type, M array to int to int. Remember, no lollipops now. I've just got these kind system. I've got linearity on the kinds instead. Now consider f of n. Well, it has type int arrow int. But this function must not be duplicated because it's captured inside itself this m guy. Oh, so now this is scary, right? And so that's why I say the rabbit hole gets quite deep here. Every system that follows this approach ends up having to address this problem in some way. So I'm not saying this is the wrong thing to do, just that it's a different thing to do, and it has, although it is the first thing you would think of, it has some significant problems all of its own. Okay. Let me I won't say that again. Okay, so what about this other axis here? So this I'm less clear about. I'm fairly clear about this one. I feel as if the linearity on the arrows really has fitted much better. I could be wrong, but it seems to work better. On the other axis, linearity versus uniqueness, here we're saying, look, what does this arrow mean? Does it mean, as we are saying, that the function makes a guarantee that f makes, or is it a guarantee that the caller must make to give it the unique pointer? That's what people typically call a uniqueness type system. Okay, here I don't really know. Maybe some of you know better than me, right? So linear types seem to have a quite close connection to linear logic. Maybe we just need to understand uniqueness logic better in order to understand systems like this. I just haven't found a way to make that work yet. Maybe there exists some. But perhaps this classification would just sort of help. And I think that, again, I'm on thin ice here, I think that this stuff, that Rust is more like linearity on the kinds, and that for the borrowing stuff, it's more like linear types, and for the ownership stuff, it's more like uniqueness types. If you own a type, that means you really do have the unique pointer to it. Okay, so here we are. We have, so there is a paper about this where we're busy implementing this. It's actually this is a big pervasive feature. And so here's my, here's my summary. The prototype is sort of working. There's bits that are not in the paper, like how do you do type inference? And I think that's probably not too hard. I feel as if we can tell a good story about that, but we haven't told a formal story. And then there's, what is there? There's how does the intermediate language work? And for example, I would like the GHC's intermediate language, which is successively transformed, we would like that to guarantee that the linearity guarantees are maintained. And that means that these linear types have to percolate into the language that is being successively transformed. And that's a fairly systemic change. And indeed, some transformations, like common subexpression, will deliberately, not maintain some of these assumptions. So you have to be, there's plenty of work to be done there. But at least some of it is done already because of all this polymorphism stuff. So here's my sort of conclusion slide, really, which is that this is the first time at which I feel that there's a system that looks feasible in the context of an existing language, and one that sort of goes with the grain of it, and sort of hangs together. So for me, it kind of feels right for the first time, and but at the same time, it is quite a big change, and it's a significant bump in language complexity too, that programmers trying to program with this would have to understand. And so I feel as if neither the costs nor the benefits are well characterized yet, but probably the best way to do that is to try it out. So that's what we're proposing to do. I just don't want to claim that we have the silver bullet just yet. So maybe some of you will be able to help me make the bullet more silver. Thank you.
Maybe we can have a couple of questions.
Yeah, so this is really nice. I was wondering, so you had this one axis with polymorphism on or linearity on the kind.
This one?
Yeah, right.
Yep.
On the arrows or linearity on the kind. There's another thing which is kind of like a generalization of the arrow thing, I think, which is substructural types, which would put like multiplicity on basically every type in the larger type, right?
Uh-huh. So every, in the type syntax,
Yeah.
every
On
construction
every
would
level,
have a
yeah.
multiplicity, right?
Right.
So yes, and moreover, since everything has a multiplicity, if you had a data type declaration, you'd probably decorate it with the multiplicity variables for every subterm
Right.
in the definition of the data type.
Right.
So I think I had a long time ago, I did work with Keith Wansborough on so-called usage types.
Mm-hmm.
And we indeed got data types with 60 or more arguments, right? And it just didn't, it was unsustainable. So maybe you could do something like that, but I've not seen it yet.
So you're basically saying the linearity on your arrow is like a sweet spot for that, which is a simpler system.
Exactly, because it's sort of like as soon as you see the type of fold, you would say, well, of course, in order to make these guarantees, you have to link the linearity on the function argument. It just feels like there couldn't be any more compact. You have to say at least that. And polymorphism seems, perfectly formed for doing that. So yes, a sweet spot if you like. Yeah.
Thanks.
Hello? All right, so a little bit earlier you had a definition of I/O that had a linear arrow that was consuming a world.
Oh, darn. Yes, I did.
Somewhere.
Yes.
So how does that square with, say, concurrency? Since at that point, don't you have to duplicate the world? Is that
Yeah.
just unsafe?
Yeah. Let's see. I think you're referring to something like. No, I've got it. Oh dear. Yes, good. Exceptions. It was this, right?
Yes.
Yeah. So of course, yes. Remember, this is. I would regard this as an encoding of I/O. If you look at a semantics for concurrent Haskell, it doesn't do world parsing at all. It's much more direct operational semantics in terms of monadic operations. So yes, the semantics of Haskell with concurrency certainly involves concurrent operations, and you need to think about that operational semantics. And so, but nevertheless, in the compiler infrastructure for compiling a single thread, you really don't want to accidentally duplicate that world. And so it's kind of giving a little bit more guarantees. But it doesn't explain I/O, definitely.
Thank you.
Yeah, hi.
Idris has uniqueness types, I think inspired by clean. I wonder if you'd looked at that as a possible inspiration for filling in your empty box in your
Yes. So the whole uniqueness type world is how to say this? So clean is a shining example of a language that, 20 or even 30 years ago, they had a pretty elaborate uniqueness type system that actually worked. And they indeed used this for explaining I/O, in fact. And they sort of split the world. They had world splitters and world joiners. So I think the truthful answer would be that I don't understand all the implications of uniqueness typing in the same framework as we've done it to give you a sensible comparison. So I was saying, so I know about this design space, I know about the others, but how does everything fit together? I'm waiting for Phil to tell me. There's not a very satisfactory answer, but it's a truthful one.
Hi, Simon. Thank you for the awesome talk. As a designated C++ guy here, I wanted to ask whether you have checked out the move semantics in C++ and whether...
The what semantics?
Move semantics.
The MOSE?
Move.
Move?
Like moving.
Oh, the move semantics?
Yeah.
No.
And whether it's something that I should research.
I don't know. Maybe somebody should explain to me educate me about the move semantics. Probably not in front of several hundred other people.
Of course, I agree.
But please do. Yes, I don't know about the move semantics.
Over here. Hey, Simon.
Oh, yeah, hi.
Could you please elaborate a little bit more on the levity polymorphism?
Oh, yeah. Fine. So let's see. In GHC, we have these types like int and float and list of int and maybe, and they're all lifted types. They all are represented by a pointer into the heap, right? So, and polymorphism generally works over these lifted values. But GHC's version of Haskell also supports a type called int hash, which means I am an honest-to-goodness 32-bit integer, right? And I'm not a pointer to anything, and so don't follow me in the garbage collector. And we have float hash and double hash, and also array hash, meaning I am a pointer, but I'm always a pointer to an evaluated array. So what are these unlifted types? They have a different kind, right? And their kind, in fact, you might imagine that the kind could tell you something about their representation. You might have the kind of things that are represented by 32-bit non-pointers, the kind of things that are represented by 1-bit non-pointers, the kinds of things that are represented by 64-bit float. And you see what I mean? So you could use the kind system to classify these. So we do indeed use the kind system to classify these types. But for a long time, GHC just could not be polymorphic over these levity, over these unboxed types. But then we found a way that some functions, like error, which have type string to A, well, is there any reason you can't say string to int hash? What's wrong with that? The code for error never manipulates its result, right? In fact, nobody's going to, because it's a call to error. So error can have the type, for all A that ranges over all types, not just the boxed ones. So it has a levity polymorphic type. So the levity is, lifted, how lifted it is. And there's a paper about that at PLDI last year, or maybe the year before. Look on my homepage, but it's fully implemented.
I'll have a look at that.
Yeah,
Thanks.
Richard Eisenberg is the man. He's a very clever fellow.
Hello.
Yeah.
Yeah, so before the talk, we've had a chat, and you've mentioned that the laziness story was surprisingly easy.
Yeah.
Could you speak
thank
about
you.
that a little bit?
Oh, I should have paid you for this question. So, usually in linearity systems, in a lazy language, one of the difficulties is, am I going to consume this value? You think, oh my goodness, I've got this thunk, and the value is, this thunk is returned as part of a data structure, and how am I going to know whether this thing is evaluated at all? Right? So laziness, the whole point about laziness is that it really doesn't tell you how much things are evaluated. But the miraculous thing is that laziness really didn't come up anywhere. Right? The rules that I gave you are enough just to say whether a function is linear without talking about laziness at all. So it's sort of independent of call by need versus call by value. So that was a huge relief, because I've always thought of laziness as being, well, if you want a linear language, you should really use a call by value one. But it turned out not, and that was a revelation, and I should have mentioned it, so thank you.
Isn't it showing up in your definition of what a linear function means?
Is it not showing up in my definition of what a linear function means? Well,
So you're saying it's only consuming the argument once if...
yeah, that's right. If the result is consumed once. So maybe in a call by value language you could say, I don't need to have the if part. That's
Okay,
a good
I think we have time for
question.
one more question.
I don't
We have one in the very
know
back
whether
corner.
that would work out in the end for a call by value language, but it might. Yeah.
Hey, I have a quick question about integrating with existing code. So I think at the beginning you mentioned this is going to ship as a language extension.
Yeah.
So how does code that has the language extension enabled and code that doesn't have it enabled interact? Because if I, in the code that doesn't have the extension enabled, define a function that doesn't have any linear annotations, and then want to use it in a world where I have all this linear type, how does that
Yeah,
work?
so I suspect if you, the truthful answer is I've not really thought through all of this. You could imagine various things. You could say, if you defined it in a world that didn't have linearity extensions, that's what you get, and tough. Or we could say, we will secretly behind the scenes, do the linearity analysis, but never show it to you. Generate this more polymorphic type. I suspect we'll do the former. And so if you want your functions to be, to have joyful linearity higher order properties, you may need to switch that on in the library. And so maybe library authors will start going back, adding the extension, not because they need to use it, but just so that they get more elaborately inferred types for their clients to use. Maybe.
So the one way would work, but the other way wouldn't work, right? So if I add my linearity annotations to my library and then call it from a non-linear
Oh, that will be fine.
That will be fine.
So if you have a nice thing with linearity polymorphism, we'll arrange that if you use that in a library that's not meant to have the extension, we won't say, oh, we'll just instantiate the linearity parameters appropriately.
Okay.
So that part will be fine.
Okay.
Yeah.
Thanks.
Okay, and just so that we can stay on time and get to the party venue, let's thank Simon for a very exciting talk.
Great, good.